Okay, let's dive right into this explainer. If you're tackling data structures and algorithms, you probably already know your way around basic C++ and writing out standard brute force solutions. But, hitting a wall with greedy algorithms and sorting-based interval tricks, that is incredibly common. Today, we're going to break down LeetCode 1288, remove covered intervals, and we'll visually deconstruct exactly how setting up your data structure with a clever sort can completely transform your approach.
So here's our core challenge. We've got this list of intervals, and we want to remove any single interval that is just completely engulfed, literally swallowed up by another one. We only want to keep the unique, surviving intervals that stand on their own and figure out the count of those survivors. But doing this efficiently, yeah, that's where things get kind of tricky. It's super easy to lose track of what you've already processed or to end up comparing the exact same items over and over, which just completely tanks your processing time.
To fix this, we absolutely have to nail down the covering condition. For an interval starting at A and ending at B to be fully covered by an interval starting at C and ending at D, two rules have to be met at the exact same time. First, C has to be less than or equal to A. Second, B has to be less than or equal to D. If you picture this on a number line, the larger covering interval must start at or before the smaller one, and it has to end at or after it. It's exactly like a pair of physical brackets just trapping that smaller segment inside. We're essentially checking two dimensions at once here, the start time and the end time.
Now, if you've seen problems like this before, your brain probably jumps straight to the classic brute force approach. You know the drill. Pick an interval, compare it against every single other interval in the list, and check both of those start and end conditions we just talked about. If both hit, you mark it as removed. And hey, this is logically completely correct. It'll get you the right answer for sure. But it creates a massive O(n)(squared bottleneck. I mean, if you're dealing with 1,000 intervals, you're looking at roughly 1,000,000 comparisons. It's painfully slow because we're basically treating the data like a totally random pile of sticks instead of actually organizing it.
So let's work smarter and reduce the problem. What happens if we just sort the intervals by their start time in ascending order? Well, by doing this one simple structural step right up front, we actually get that first covering condition completely for free. Think about it. If we process these sorted intervals from left to right, any interval we look at is mathematically guaranteed to start at or after the ones before it. Boom! We've structurally satisfied that C is less than or equal to A requirement without writing a single extra loop. We just took a messy two-dimensional problem and flattened it into a super clean one-dimensional sweep. Now we literally only have to care about the end times.
But wait, what if the start times are exactly identical? This is where a lot of people get tripped up, and it's why we need a very specific tiebreak rule. Let's take intervals 1, 4, and 1, 2. Since they both start at 1, a basic, naive sort might just throw 1, 2 first, and that is a total disaster for our sweep. We'd process 1, 2, assume it survives, and then hit 1, 4 right after, totally missing the fact that 1, 2 should have been covered. To fix this, when start times tie, we have to sort by the end time descending. This explicitly forces the larger, covering interval, the 1, 4 in this case, to be processed first. It ensures we cast the biggest net possible before we start looking at the smaller fish.
Let's actually sweep through a concrete example so you can visualize this on the number line. Imagine our sorted input is 1, 4, 2, 8, and 3, 6. We kick off our sweep with our very first sorted interval, which is 1, 4. Because it's literally the first thing we're looking at, nothing could possibly be covering it yet. We're going to use a running tracker variable for our furthest reach, let's call it maxEnd, and initialize it to 0. Since our current interval's end is 4, and 4 is greater than 0, this interval survives, it's uncovered. So we dynamically update our maxEnd tracker to 4 and keep moving. Next up in our sorted list is 2, 8. Now, remember our sorting trick? We don't even need to look at its start time of 2, because our sort already guarantees it started after the one we just processed. We only care about that end time, which is 8. So we ask, does 8 reach further right on our number line than our current maxEnd of 4? Yes, absolutely. Because it stretches further, there is no physical way it's covered by the previous interval. It survives. We update our maxEnd from 4 to 8, meaning 8 is our new furthest reach. Finally, we hit the third interval, 3, 6. Once again, skip the start time. Look straight at the end time, 6. We compare 6 against our current maxEnd, which is 8. And check this out, because 6 is less than or equal to 8, the interval 3, 6 gets completely swallowed up within the bounds of our previous furthest reach. It doesn't poke out past 8 at all. So it's covered. We can confidently skip it, mark it as covered, and move on. Notice how we did that without writing a single nested loop to look backwards?
And that brings us to the absolutely beautiful core invariant of this entire algorithm. If you remember literally nothing else from this explainer, let it be this. Because of our initial sorting strategy, just checking if the current interval's end is less than or equal to our max end is mathematically and computationally equivalent to checking both of those original clunky covering conditions. The sorting algorithm does all the heavy lifting for the start times, and our one little max end variable compresses the entire necessary history of the end times into a single integer. Just look at the massive difference we've made simply by organizing our data first. We've taken that sluggish O of n squared brute force nightmare and transformed it into a super sleek O of n log n sweep. Plus, aside from the standard memory used by the sort itself, this sweep requires only O of 1 constant extra space, since we're just updating that single maxend integer. It is a game changer. So here's a final thought to chew on as you keep learning DSA. If a clever sort can so beautifully collapse a complex two-dimensional interval problem into a single one-dimensional sweep, what other multi-dimensional brute force problems out there are just waiting for you to organize their data first?